Alright folks, welcome back to Moonshine Radio. Today we're going to do a talk on antenna arrays. Now often people do videos on this topic and they start with a lot of mathematics and a lot of crazy equations, and really all that's there to confuse you and make you not learn the topic. So today Dr. Moonshine's going to approach this from a much simpler angle, and hopefully you're going to get the basic concepts of antenna arrays. And once you know these basic relationships, I think then you can dive into the deeper mathematics to understand how it all works. All right, so the first thing you have to realize is that one wavelength is equal to 360 degrees, okay? Such that half a wavelength is now equal to 180 degrees. And this is a very important concept to understand. And so obviously the wavelength is related to whatever frequency you're transmitting. All right, I think that's pretty straightforward. So knowing that, the idea that you have to understand is if you have two signals that are both in phase, and you add them together, what you get is a bigger signal. This is what's called constructive interference. They basically constructively add together and you get a bigger signal. All right? So the opposite of that is if now you have two signals that are 180 degrees out of phase with each other. And if you add those two signals up, you will get no signal. And this is what's called destructive interference. So those two ideas right there are the critical building blocks of what an antenna array is. All right. So knowing what I just talked about, let's get into our example. So here we have essentially a bird's eye view of a two antenna setup. So we are looking down at these two antennas. They could be two dipoles, two monopoles that are both vertically polarized, and we have two positions, A and position B. These are two positions in the far field from these two antennas. And these two antennas are hooked up to one signal generator at frequency F0. It goes through an RF power splitter. This is not a T. This is a true RF splitter. It then goes into two coax cables of equal length, X, and the two antennas are separated by their wavelength over 2 spacing and distance. Now remember, wavelength over 2 is equal to 180 degrees. Like I said, that's a key thing to remember. So let's look at the signal at position A. Well, we will have both signals leaving those antennas. They both propagated the same distance. So I think it's clear at position A, we will see a max signal. Why? Because 0 degrees plus 0 degrees equals max signal. So if you had a radio at position A and tuned to frequency F0, you would hear the signal no problem. Now we're at position B. This position, you would see a very weak signal, if not no signal. And why is that? Because those two signals are now 180 degrees apart. And like I said, when two signals are 180 degrees apart, they cancel and you get no signal. Why are they 180 degrees apart? Because the two antennas are spaced wavelength over 2. And what is wavelength over 2? 180 degrees. So to say it simply again, position A, we see the max signal. Position B, we see the minimum signal. So that is a very basic two antenna array. And again, this is a bird's eye view looking down at our two vertically polarized antennas. They could be a monopole, a quarter wave. The point is both those antennas have to be the same antenna. Okay? So hopefully that's Fairly straightforward. All right, now let's add an additional 180-degree phase shift to one of the antennas. Now what happens with position A and position B? Well, now position A sees a 180-degree phase shift. So 0 plus 180 degrees is no signal. It's going to destructively add together and essentially cancel each other out. So now position A, we will see no signal. Now at position B will be the max signal because we have 0 plus 360 degrees. We have 180 on the phase shifter, and because the two antennas are spaced wavelength over 2, you get 180 plus 180 is 360. 360 degrees is also the same as 0 degrees. So those two sine waves will add together so that now at position B, we now see the max signal, and position A, we see the minimum signal. So simply by adding a phase shift has essentially allowed us to steer the beam of where the signal is going to radiate from this simple two antenna array. And hopefully you can see that if we've added more antennas, we would get a finer and finer, narrower beam with much more fidelity. But today we're keeping it real simple, and we're just talking about a two antenna array. So hopefully you see there, by adding that 180-degree phase shift has allowed us to electronically steer the beam to max signal at position B and minimum signal at position A. That is the basic of antenna arrays. Now, I've shown this in a transmission case. This same idea could be used in a receiver case where either A or B now is your signal that's transmitting and you're using the two arrays for receive. It works either way. I'm just showing a transmission case, but it's the same logic. If position A or B were to be transmitting, you can also make this antenna array to max pickup signal either A or B, right? It works either way. All right, now we're going to get into the modern approach. This is how this is working in today's world. Rather than having one signal that we're analog splitting and using analog phase shifters, that's kind of a 1970s approach and highly outdated. But anyway, the 21st century approach is now we have two digital to analog converters, both running on the same clock frequency, both aligned, and they are now connected directly to those two antennas. The two antennas are still spaced wavelength over 2. And now, because it's all digital data, hopefully you can see now that with this setup, I can have signal A be at F0 and put its signal max at position A. And I can have signal B, because I'm adding that 180-degree phase shift to the one DAC, I can put his signal to be max at position B. And this can be all happening at the same time. And this is what's called MIMO, multiple input, multiple output. So these signal A and signal B could be unique OFDM signals, whatever. And you betcha this is the backbone of what they are starting to do with 5G communications, where they're going to have cellular arrays on the telephone pole, and they're going to be able to have different signals at the same frequency pointing to different users of obviously different phones. And this is an idea of how they're doing that, because behind every antenna is a DAC, and you can combine multiple signals. So this basic two-element antenna has now turned into quite a powerful method to give a unique signal at position A and a totally different signal at position B, all by using basic antenna array theory. Well, Hopefully that was a very brief introduction to antenna arrays. Obviously it can be expanded much more. The more elements you add in the array, the more finer the beam is and the better you can steer it, blah, blah, blah. Also, the better you can cancel signals of interfering signals. But hopefully I've shown just with two simple antennas combined together, you can make a very basic antenna array. Well, hopefully that was simple enough for you, and you learned something today about antenna arrays. Live from Moonshine Radio University, this is Moonshine Radio.